Have you ever sat in a parked electric car wondering what's going on behind that shiny front end? What's powering those sleek-looking wheels? Well, today we're going beyond the glossy surface of electric vehicles to uncover the secrets that make them go. Buckle up, because we're about to take a ride through the inner workings of an electric car. Now, before we dive into the heart of the electric car, let's take a quick look at its most recognizable feature: the battery pack. Electric cars have got a lot of batteries, not like the small ones in your TV remote, but large lithium-ion cells packed tightly together to form a massive rechargeable battery. This battery pack is like the fuel tank of a regular car, but with a twist. Instead of holding gasoline, it holds electrical energy. This energy is stored in thousands of individual cells, kind of like a honeycomb, all working together to power the car. Each cell has a positive and negative terminal, and during charging, chemical reactions within the battery cause lithium ions to flow from the negative to the positive terminal. This flow of ions is what creates an electrical charge, storing potential energy in the battery. When it's time to drive, this stored energy gets released and powers the car. Alright, we've got the energy stored, but how does that energy turn into motion? Let's check out the motor. The electric motor is the part of the car that converts electrical energy from the battery into mechanical energy to turn the wheels. At first glance, it might seem simple, but there's a lot going on inside. Most electric motors, especially in EVs, are called AC induction motors, but you can also find DC motors. The main difference between them is the type of electrical input they need. DC motors run on direct current, which flows in one direction, while AC motors run on alternating current, which periodically reverses direction. Now, both types of motors work by using magnetic fields to spin a shaft. However, the specifics of how they achieve this are quite different. In a DC motor, when electricity passes through coils of wire in the motor, it creates magnetic fields. These magnetic fields interact with magnets on the motor's shaft, causing it to spin. As the shaft spins, it's connected to the car's wheels through a gearbox, which transmits the rotational motion to the wheels, making the car move forward or backward, depending on the direction of the current. AC induction motors work a bit differently. Instead of using permanent magnets, they use electromagnets, whose magnetic fields can be controlled by varying the input AC power. By changing the pattern of magnetic fields around the motor, an AC motor can make the rotor spin. Just like a DC motor, the rotor is connected to the wheels through a gearbox, and that's what turns the wheels. AC motors are popular in EVs because they tend to be simpler, more efficient, and can generate more power than DC motors. Plus, the batteries in EVs produce AC power, so it's a natural fit. Okay, but we've got a problem. The battery produces direct current, DC, but the motor needs alternating current, AC. So how do we make that switch? That's where the inverter comes in. Think of the inverter as the translator that converts one language into another, in this case, DC from the battery into AC for the motor. It's a crucial component that allows these two systems to work together. The inverter does this by switching the direction of the current flow very rapidly, creating an alternating waveform. This rapidly changing current is then sent to the motor, which uses it to spin and ultimately drive the car. Inverters are not 100% efficient, meaning some energy is lost during the conversion process, typically as heat. This is one reason why EVs are slightly less efficient than internal combustion engine cars. Okay, so now we've got the battery power flowing to the motor, but how does that turn into motion? To understand that, let's explore a bit of physics. When electricity flows through a conductor like a wire, it creates a magnetic field around the wire. This magnetic field has a direction, and it's this magnetic field that's harnessed in electric motors and generators. Here's how it works. When electricity flows through the coils of wire in an electric motor, it creates magnetic fields around the coils. If you put a magnet near these coils, the magnetic fields of the coils will interact with the magnet. This interaction, specifically the opposing magnetic fields, will try to push or pull the coil. This force is what's harnessed to spin the motor's shaft. By controlling the flow of electricity through the coils, you can control the strength and direction of the magnetic fields. And when combined with strategically placed magnets, this can make the shaft spin continuously. And guess what? This spinning shaft is what ultimately turns the car's wheels. It's like a well-oiled machine, except there's no oil needed. That's the basic principle behind how electric motors work. Another key part of the equation is understanding torque. Torque is simply a twisting force that causes an object to rotate. For example, when you tighten a bolt with a wrench, you're applying torque to the bolt. In an electric motor, torque is what makes the shaft spin. More torque means more power, allowing the car to accelerate faster or go up steeper hills. Electric motors have a lot of torque, delivering maximum torque instantly. This is unlike internal combustion engines, which take time to build up torque. The electric motor is connected to the car's wheels through a transmission system, often a single-speed gearbox. The gearbox is there to increase the motor speed to the appropriate range for driving. Electric motors spin at high RPMs, but the car's wheels need a much slower RPM for driving, so the gearbox makes that adjustment, providing the right amount of torque to the wheels. Okay, we've got the motor turning, but how does that translate into movement for the car? That's where the axle and wheels come in. The axle is a rod or shaft that connects the motor or gearbox to the wheels. When the axle rotates, it turns the wheels, causing the car to move. It's a pretty straightforward concept, but crucial to how the electric car moves. Now, the tires, of course, play a big role too. They're responsible for gripping the road and converting the rotational motion of the wheels into movement forward, backward, or sideways, depending on which motor is engaged. What about when you need to slow down or stop? That's where the brakes come in. Electric cars have both physical brakes and regenerative braking. Physical brakes are the same as in any car, using pads and rotors to slow the wheels. When you press the brake pedal, it activates these brakes, bringing the car to a stop. Regenerative braking is unique to electric cars. It uses the motor to help slow the car. When you lift your foot off the accelerator or apply the brakes, the motor can turn into a generator. This means that instead of using electricity, the motor starts using the rotation of the wheels. As the car slows down, the motor converts the kinetic energy of the spinning wheels back into electricity. This electricity is then sent back to the battery, recharging it. This not only helps slow the car, but also recharges the battery, increasing efficiency. Well, folks, we've taken a deep dive into the inner workings of an electric vehicle. From the battery to the motor, we've seen how these components work together to turn electricity into motion. It's a fascinating process and a testament to human ingenuity. If you found this journey through the inner workings of an electric car helpful, consider subscribing. Your support helps us continue to break down complex topics, making them easy to understand.